So we are here to do the experiment of Young's modulus to find the Young's modulus of a wood sample by bending of beams method. Okay, we are going to use this method of bending of beams to find the uh, Young's modulus. All right. So we have done little changes in the experimental setup. Instead of using traveling microscope, we are just using a ruler. Okay, because some of you guys had some of your friends had done this offline at the laboratory, and to avoid COVID infection, to follow the protocol, we said instead of using traveling microscope where you will have to come in contact with the will have to use your eyes very close to the eyepiece. Okay, so to avoid that, we had come up with this method of doing it using a ruler. Okay, so remember, otherwise it is done with traveling microscope with much more accuracy. All right, but anyways, we have got quite a good reading here also. Let's see. All right, so before I again start with the experiment, just 2 points to discuss. What's Young's modulus? It's a measure of the ability of the material to withstand changes in a length when under lengthwise tension or compression. So you compress or you put tension on it, how much can it withstand these changes is what Young's modulus is, and that's why it is also called modulus of elasticity. Okay, all right, so steel is a very elastic material because it withstands the changes quite well. Fine. So straight away, let me not waste. Yeah, of course, it is named after the physicist Thomas Young, who calculated these values first. All right. And let's not waste time. Let's go straight to the experiment. I will not go much in detail about this thing. I'm sure for your lectures or somewhere it is discussed and you know about it. All right. So aim is to determine the Young's modulus of the material. The material is a wood beam. Okay, that is given to you by the method of bending. Okay. Now, apparatus are material in the form of a beam, of course. Whatever materials you want, we have given you wood. All right, for this experiment, because if I had given you the knife, these steel ones, then possibly we would have not been able to see the bending at all with the ruler. All right, for that we would compulsory need a traveling microscope. You need two knife edges so that you can suspend this beam, then hanger with hook and pointer. Okay, I'll explain you what that is. Then weights, it's also called slotted weights. Okay, then scale fixed in vertical position, and micrometer screw gauge to find the depth of the beam, wooden beam, vernier caliper to find the breadth of the beam. All right, these are very two important formulas that you will have to remember, that Young's modulus is equal to acceleration due to gravity. We are dealing in centimeters, so acceleration due to gravity G will be equal to 980 centimeters per second square. Okay, otherwise it is 9.8 meters per second square, so we are using 980 wala, because we are using all other length and breadth, the depth, everything will be in terms of centimeters, and weight are also in grams, so we will be using 980 centimeter per second square. Fine. So L is the length of the banding that we will be doing. Okay, we'll be giving you a beam of 1 meter long, but the knife edges or the tension on which we will be applying will be about 70 centimeter. Then B is the width of the bar and D is the depth of the bar, the thickness of the bar. Fine. M is for mass, E is for the depression. Okay, I will tell you what this depression is. Now, same value can be calculated with all these quantities remaining as it is. Okay, all these quantities will remain as it is, but instead of M upon E, we will plot this mass versus depression on a graph paper and find the slope of it. And we will see how much different we get the Young's modulus in the two different forms. All right. So the diagram, this is the diagram that you will be drawing. Okay, this is the diagram that you will be drawing, and this is how it will look when you will do the experimental setup. Okay, so you will have these knife edges at the two ends, which is at a distance of 70 centimeter. All right, and this is the hook, all right, on which we have this. Okay, this itself is 200 grams. Okay, this itself is 200 grams, and these are other slotted weights which are 200 grams each. Okay, 200 gram each of them. So we will be doing loading unloading for almost total 1000 grams. Fine. And this is the ruler. Okay, this is the ruler that we have fitted. So This is a very pandemic specific experiment that we are doing. So instead of this ruler, we actually have having microscope focused here, and which actually finds the bending of the beam very accurately. It does it, okay, whereas this ruler is just to avoid the traveling microscope for now, as of now. All right, so that's the experimental setup. These are the weights that we are going to use. Okay, so nothing much. We can straight away go to the laboratory and see how we can do the experiments. Let's perform this experiment, okay, and come back to do the calculations. Fine. All right, so now we are at the experimental setup of bending of beams. Okay, as you can see in your video recorder, on the right side of your video, you can see that there is a scale which I have focused using a camera, so you'll be able to see the readings that I'm taking also. And also, this is the setup. You can see this is the knife edge here, the two knife edge on which this beam which is given to you, the wooden beam that is given, nothing but it is just a 1 meter long ruler of wood, okay, of that beam will be resting on that. Okay, but before that we have to do certain calculations. For example, the depth and the breadth, okay, which we will do now, and I will show you a closer look up. What we will do is we will use the micrometer screw gauge, all right, to measure the depth, the thickness of this ruler at 3 different points. Okay, so maybe we can take the reading here and then here and then here. Okay, and then we will also use the vernier caliper. We can use the vernier caliper to find the breadth of this beam, again at 3 different points. Any 3 different points, it's up to you. Any 3 random different points you can take the readings at. So we will do that, and then we will start our experiments. Fine. Okay, so the reading that I get here is 0.55. Okay, 0.55. Okay, so note it down. The reading on the main scale is 0.55, and the circular scale reading is I hope you can see them. Okay, the circular scale reading, if I just turn this bit to show you, all right, it's around 16. Okay, similarly we'll take two more readings at 2 different points. Okay, so I hope you can see this. So main scale reading is again 0.55, and circular scale reading is almost 34. Similarly, let me take one more reading at another end. So again 0.55. 0.55, and the circular scale reading is around 18. So we have used the screw gauge to find the 3 different readings at 3 different points of the scale. Similarly, we will use the vernier caliper. We will now use the vernier caliper to find the breadth of the scale. Okay, so what we do is now, again, you can see the vernier caliper. The smallest reading on the vernier caliper is again 0.1, and the number of divisions on the vernier scale is 10. So that will help you to find the least count of this instrument. Okay, so again, let me take at some almost similar point 3 different readings. Okay, so I just take it out, and you can see I hope you can. It's not so clear, but you can good enough to see the reading. So the main scale reading is around 2.6. Okay, the main scale reading is around 2.6. I'll note it down here. And vernier scale, that is the scale number that is coinciding. Okay, coinciding on the ruler on the vernier caliper is 2. Okay, is 2. So that's noted down. Again, I take another 2 reading at 2 different points. Okay, again I take 2 readings at 2 different points. So I just take it out for you to show. All right, so it is 2.6, and the vernier scale reading is again around the coinciding one that you can actually see is around 6. All right, so let's take the third one. Let's take the third one. Okay, push it in. And let's take the reading here. I hope you can see on the screen. These 2.6. And the coinciding reading is around at least what I could see is around 8. Yeah, all right, so I just note it down here. And what we'll do now is that we go ahead and do the remaining part of the experiment. Fine, all right. Fine, so now since we know the depth and the breadth of this cantilever, the beam that we are given to us, that is the wooden beam that is given to you. Next thing, before we start the experiment, one more thing that we need to do is we need to find the center of mass of this particular beam. And for that, what you're given is a knife edge. Okay, and you keep this knife edge here. And what you could do is take this beam, the wooden beam that is given to you, and place it in such a way. As you can see, right now it is not placed properly. So you can see that this particular beam is bending towards this side completely. So what I do is that means there is more weight this side and less here. So I try to balance it to get the proper center of mass. It is not yet done, so I just move it a little bit more. Okay, fine. So as I can see that this is almost balanced now. Okay, almost you can see this totally balanced here, correct? Okay, so at this point what I do is I put a marking with a chalk. With a chalk I will put the marking, and right at that point will be the hanger with a weight. The hanger that will be holding the slotted weights will be resting. Okay, at that point. Now the bending length that we are going to use is 70 centimeters, and because of that we will have to take 35 centimeters from this point and 35 centimeters from this point, and these will be the point where the beam will be resting on. Okay, so this will be the point where the beams will be resting on. Okay, so at 70 centimeter length the beam will be resting on the knife edge. So I do this marking. It's quite easy when I'm using this kind of a ruler because there is already a marking here. So I can see the center of mass is around 50, yeah, 49.5 rather. Okay, 49.5. So what I do is I move 35 centimeter from here. That is 84.5. So that is somewhere here. 84.5 is here. So I do this marking right here so that I know the mark. And again I move from here 35 centimeter. So that would be around 14.5. So just do this marking here. So I've got the two ends. On which this knife edges are going to rest on. Fine. So what I do next is I just bring this beam here. Okay, and I place on the knife edge. All right, I place on the knife edge. Okay. And also next what I'll do is I'll take this hanger on which the slotted weights are going to be resting on. All right. The slotted weights have a knife edge here. So that knife edge will be coming on this point where we have marked the center of mass of this particular beam. So we just bring this here down, keep it, again rest it at the length of 70 centimeter and place it here. Fine. Now in your ruler, if you could see this, you can clearly see there is a pin here, right? There is a pin here. Okay, so I can just make this little adjustment for you a little bit more. Okay, so that you can see it much more clearly. All right, so you can see this pin, and this will be your reading for 0. Okay, so this hanger with a pin is your first reading for 0. All right, and now we are going to take the reading for loading, and of course followed by the readings for unloading. All right, now we have this hook, okay, which we will put it on that hanger. Okay, and then all the weights, other weights for loading will come into this. Fine. Okay, now each of these slotted weights that are given to you are 200 grams, 200 grams, and this one is also 200 grams. Now this thickness is little lesser than the slotted weights that is given to you. That's because this holder which is there for it, will take care of that remaining mass. Okay, so that's why this is little thinner compared to the, I don't know whether you can see it clearly from the camera, but it is little thinner, okay, compared to this one, because this is the extra weight that it will take care of. Okay, all right, so what we do is now before we place that, we will start taking reading, and this will be your reading for the 0, 1. And if I have to go with you, the reading that you can see on the scale is, okay, the reading that you can see on the scale is, yeah, so the reading that you can see on the scale is 35.7. All right, yeah, it's 35.7. So let me note it down, and you can also note down at the same time. So 0 is 35.7, okay, grams. So I've noted down the reading for the 0, 1. All right, now I take this hanger, which is 200 grams, and now I just place it here. So the moment I do this, I hope you can see in the video also that the scale reading has come down, okay, to 35.4. 35.4. So we note down that reading for 200, that is 35.4 grams again. All right. So this is a very simple experiment. All that we are going to do in this procedure is just add up the weights now, okay, and in the unloading one we are just going to remove the weights. That's it. All right. So I take the next 200 grams and I carefully press this. And as I do that, I'll just go by what you can see on the camera, and that is 34.4. Okay, 34. Sorry, what you could see in the camera, 30, not 34, 35. 35.2. All right, so 35.2 grams. I go for another 200 grams. This has come to 34.8, right? 34.9, in fact, it's quite clear here. 34.9. All right. I don't know whether this, yeah, this will help you a little bit more clearly to see it. 34.9, because I just put on the lamp for you. Next, I'll put in another 200 grams of weight. Now that makes it 800 in total, and the reading is 34.7. I hope they can also see the same thing on the scale, 34.7. And finally, I have another 200 grams that I'll add here. It's 34.4. I hope you can also see that. That's 34. Looks like 34.5 in this video. Yeah, it is 34.5. Fine. Okay, so now we'll start unloading them, because we have two sections. One is loading and other one is unloading. So we now try to unload it. So I take off another 200 grams from here. Okay, keep it aside, stabilize this. So if I go by, it will be 34.8, 34.7 here, 34.7. Okay, so 34.7. That, I mean, also remember 1000 loading and unloading reading for 1000 will be same. So I will write 34.5 with the 1001. Okay, then 801 will be 34.7. Okay, 34.7. Next, we will take off another 200 grams. So I have this reading which shows 34.9. You could also see that it is 34.9 on the scale. 34.9. Okay, all right. I'll take out another 200 grams from here. I'll stabilize this weight. So this will be 35.2. Okay, so this will be, I hope you can see that clearly, it's 35.2. And then we have this 200, another one, so 400 reading. So we take that off and stabilize this. And this is 35.4 here, and I think you can also see on your scale it looks like 35.5. It's a little bit 35.4 and 5 in between kind of, but I will take it as 35.4. And finally I'll take off this 200 grams also for the 0th reading, and This is 35.7. All right, 35.7. You can also see in your video there. It's 35.7. Fine. Okay, so with this we have done the experimental part. Remember, we are doing this experiment because of the situation, that is the COVID situation. A part of you who had come to the practicals for offline practicals, we have made you do this, and to avoid the use of traveling microscope, we were using this method. Okay, the proper method to do this is using the traveling microscope, where you will get much more uh, accurate reading. Now if you see the reading, it is almost repeating for loading and unloading. That would not happen if you are using a traveling microscope. You will see these minor changes that is happening with addition of weight or reduction or loading or unloading of weights. Fine. So that is not happening here because we are using straight away the scale reading, which error is just the least count of which is just 0.1. Okay, fine. So what we'll do is now go back and do the calculation for this experiment, and let's finish this experiment. Okay. All right, so we are back with our data. So as I told you, the length of the knife edges, the length of bending would be around 70 centimeters. Okay. The width of the bar B, would be using the vernier caliper, as you have seen in the video. And I've just done these calculations. It was 2.6 consistently, but the vernier scale readings were changing. And vernier scale is multiplied by the least count. Least count was 0.01. And this is the final readings that we have got, of which we add all three data and divide by 3 to get the mean. Okay. Similar process for micrometer screw gauge. Okay, instead of VSR we have the circular scale readings there, and luckily the screw gauge was on 0, so not much errors to be added and subtracted, so that job is not there. So straight away we could write this reading here, and the thickness of it was found to be, if you average, add and divide by 3, you will get this value for the thickness. Fine. Okay, so this was the initial calculations that we did before starting the experiment. And then we have yes, this is what we have already found. Already told to you that the distance between the knife edge is 70 centimeter. This is what we have already calculated. The width, okay, the breadth of the beam, the bar that we are using is 2.65, and thickness. So all this is calculated. So now our data is here that we've just found. So here we have 0. We started with 0, went up to 1000. So add up all this value and divide it by 6 to get 500. That is mean. Then we have this loading unloading values. Now unfortunately, because we are not using traveling microscope, a ruler which is having error of plus or minus 0.1 is just giving you same to same reading as you are changing. Now if you use traveling microscope, you get very good readings, very good variations you can see as you are loading and unloading. Okay, now because you have got same to same reading, you will simply write the same values in the mean also, because adding and dividing by 2 will give you the same value, will not give anything different. All right, next. So yeah, all right, so in ruler also, if you had got now the scale that we are used, even if you had got some different reading, you would have added them and divided it by 2. So that's what is mean. Okay, I don't have to tell undergraduate student what the mean means. Okay, so just add it and divide by those any number. So here there are only 2 values, so just add and divide by 2. Now most important part is this depression, how to calculate this value of depression for mass M. All right, you need to take this value 35.7 every time and subtract the next value with the value, okay, every time. 35.7 minus 35.4, 35.2, 34.9, and so on. So obviously the first value will be 0, because 35.7 minus 35.7 will be 0. Let me just do it for you. 35.7 will remain constant every time, minus 35.7 will be 0. Next again 35.7 minus 35.4 will be 0.3. Then we have 35.7 minus 35.2 equal to 0.5, and so on. Okay, that way you will get all these values of depression. All right, so what you do next is add them all up and divide by 6. You will get the mean value of depression. All right, okay, so that's it about what you can do with the data that you obtained. So we straight away go for calculations. We have this formula which I have already discussed with you right at the start. Okay, so now in this formula it's time to put the values. G is 980 centimeters per second square. Length is 70 cube. 4 into the breadth and depth values you can put, which is cubed. Be careful, it's cubed, multiplied by the mean value of the mass 500 and mean value of the depression 0.63, and this turns out, just punch all these numbers on your calculator and cross check, this turns out to be 1.33 into 10 raised to 11 dyne per centimeter square. Okay, 1.33 into 10 raised to 11 dyne per centimeter square. Very nice value. Okay, for wood of this kind, the Young's modulus is around 1 to 2 dyne centimeter square. Okay, 1 to 2. So we have got 1.33. It's a very nice value. Okay, next what you could do is plot a graph of the values that you got from depression of the beam and the masses. Okay, so both the values you can just plot. You'll get a graph like this. Remember the scale. To write your scale, 1 unit I have taken 100 grams. You can take what you want, your preference. 1 unit is 0.1 centimeter of depression I took. Okay, so find the slope. I got slope as 1.55 into 10 raised to 3, and see that your graph that you draw on your journal contains all this what you have done in this graph image that I've shown you. Okay, so from the graphical method, all these value remains as it is, just that instead of m upon e, we have the slope of the graph, which is 1.25 into 10 raised to 3, and which we just put in the value. We get 2.11 into 10 raised to 11 dyne per centimeter square. Not same to same value, but quite good value in both cases. Okay, graphical and experimental in this kind of experiment do come little different. All right, but both values are quite good, I would say. Okay, both values in terms of Young's modulus for both of them are very good. Okay, very impressive values. All right. So next you just write the results finally. Okay, you can write what you got from experimental values. Okay, that it is 1.33 into 10 raised to 11 dyne per centimeter square, and what you got from graphical methods, that is 2.11 into 10 raised to 11 dyne per centimeter square. Fine. And with that we finish your Young's modulus. How to find Young's modulus using the very innovative way that we did now, that is to find the without traveling microscope. Okay, so I hope you enjoyed this experiment, and hoping to meet you soon offline, or if online then with some other experiment. Fine, so see you soon. Thank you.